We are resuming our the seminar and discussion series, and we are very happy to open the season with Siddhant Das, who is going to tell us about relativistic electron wave packets for spin-dependent arrival time distributions. Go ahead, Siddhant.
Thanks so much for having me once again in the seminar. And I hope you can hear me well. I still feel like my internet is a bit not great, but in case I'm gone, just let me know, or maybe I'll just switch off my video at one point. So let me jump right in, if you can all hear me and see me well.
Yeah, everything is fine. Oh.
Okay, so this talk is kind of a continuation of the kind of talks I've given before at this seminar, and that's why there's not too much background being covered once again, because I can see most of the people present here know the background, but I'll still motivate the reason for a relativistic analysis of the experiment that we have been talking about. And then I'll go on to present whatever I've done so far in that direction. So this is really unpublished and fresh stuff. There would be mistakes, so don't take it for granted. Everything is correct, and please feel free to ask questions at any point. All right, so just to have a common ground for everybody, let's begin with the usual analysis you find in textbooks of a scattering experiment, a quantum scattering problem. Okay, so not every textbook these days mentions it, but there are a few, at least books like Owen Tanuji, for example, would say that the probability that in a certain patch of a detector surface you have detection between time t and t plus delta t is given by this expression. I just wanted to know how many of you have seen this other than Shelley, this kind of an expression in, is there a way to like take a poll or something, or? Hello?
People can react.
I've seen it before.
Yeah, so surprisingly, I have seen it only one of the textbooks at the moment, and I would be happy to know if you can give me some additional references. But this formula, not everybody mentions, and there is, of course, reasons for it. I mean, one of the reasons simply could be that they haven't seen it.
This textbook that you met, Cohen Tanucci, you say they have this formula, right? They have this formula.
Mm-hmm.
How do they motivate it, or do they try to derive it from the usual axioms of quantum mechanics? Is it an additional axiom? What is it for them?
So this quantity, this is supposed to be a differential probability. It's actually a joint probability according to books even, for a detection in an area element ds, and the detection taking place between time t and t plus delta t.
Yeah, I know
as far as I...
But the question is not what it is, but on what basis they argue for it. Do they try to derive it from the standard quantum axioms? Do they present it as another axiom? What?
So the thing is, they do not derive. I was actually coming to that. So there is no derivation of it. It's explicitly stated as an obvious thing, as is usual in quantum textbooks. And then they go on from here to derive the famous formulas for scattering cross-section. I would be totally surprised if they could even motivate it from any quantum axiom, to be honest. The reason is simply because this cannot even be a meaningful probability in every situation, right?
Just don't have to
So
be meaningful to be motivated.
somehow I can't hear you, Shirley, and maybe
Can you hear
so
me
the
now? Can you hear me?
yeah, I could hear you. Can you hear me
Well,
now?
I just said that things
Yeah.
do not have to be meaningful to be motivated.
Ah, okay. Hello.
Here,
Yeah, somehow I just couldn't hear any sentences for a second or two.
I didn't
Could
say anything after a very brief statement.
Siddhant, just move on.
Okay. So this is my favorite starting point, because I think in a standard textbook there would be really no way to derive it. I mean, one could take it as an additional axiom, but of course, such a probability assignment will not be consistent for every wave function. First of all, this J is the probability current, and I wrote down the familiar expression that you find for Schrödinger equation. And there is one reason why people need an additional postulate in scattering experiment, because in the usual textbook analysis, one always deals with wave functions that are not normalizable. I mean, this is known to everybody, I presume. So that's why I wrote in this gray ink here, kind of form of the wave function one sees in the textbooks. Now, we all can see that if you square this and try to assign probabilities by Born rule, you will not get meaningful probabilities. It's not a normalizable wave function. That's one of the reasons why I think people end up using this additional probability assignment. But then fewer still know that this cannot be a meaningful probability density for every wave function. And the reason is this quantity can just be negative. So there are wave functions for which the probability current can be pointing, let's say, opposite to the direction of the surface ds, for which in which case this can become negative.
Isn't the reason you can't use Born's rule more basic than that? Born's rule doesn't say what operators is it supposed to correspond to. It doesn't. Born's rule doesn't apply.
I was coming to that, really, even. So that's the second reason for why they need an additional postulate. And the second reason is not just that, the wave function is not normalizable typically in these examples, but also because the Born rule does not give us probabilities of this kind, right? So Born rule gives us at a given instant of time, where is the particle in space, right? It gives you the probability density of position.
Be a bit more patient.
Right. Whereas this quantity is supposed to be a joint probability of a detection on a specified location in space and in a given small interval of time. So there's already a big difference between the kind of probabilities you get from Born's rule and the kind of probability assignment we are talking about here. I mean, that of course is the real difference. Is that what you had in mind, Shelley?
Yeah, a real problem is less the technical problem of the non-normalizability of the wave function.
Yeah, I absolutely agree with you. So these are good reasons to expect such a formula, to expect why such an extra probability postulate would show up in textbook quantum mechanics. But as I was just saying, this formula is not meaningful for all wave functions, and there are examples one can construct for which this quantity can just become negative. Now, this condition is from Shelley, Detlef, and Nino. I haven't seen it in other papers. I mean, I have seen it in your papers. And, it's just an obvious consistency condition one will write down. If you have a detector surface D, so the script D stands for a geometric surface of the detector. And under this condition, that is for all time and at every location of the surface, if this quantity J dot D is positive for a particular wave function, then it seems like you could use this formula for probability assignment. Actually, it's not just the positivity that's good. I mean, as soon as this current positivity condition holds, this in fact is a meaningful probability density. You get probabilities less than 1 and so on. And these are automatically coming along with it. Okay, so it's not just something becoming positive and negative that decides whether it's a probability or not, but it's even consistent as a probability assignment under this current positivity condition. All right, so okay, now I can. As soon as this condition holds, and the question that typically Detlef and I are interested in is the detection time alone. So we are interested in not where the detection takes place on the screen, but rather when the detection takes place. So what one could do is one could just integrate this differential probability over the surface of the detector, and that would just give you the probability of detection time, or the probability density of detection time that I've written here. This is usually called nowadays pi QF, which stands for the quantum flux arrival time distribution. So I'm going to use the word arrival and detection time a bit interchangeably for the moment, but I know that there are differences between them, but we'll not get into them right away. Now, the wave functions for which this current positivity condition is violated are difficult to find. But in principle, they exist, and such states are nowadays called backflow states. And there is much interest in trying to come up with these kind of wave functions. But if you read, again, the scattering papers of Shelley, Detlef, and other people, also in the mathematical physics literature, you can understand why is it very difficult to violate this kind of condition. Or I should put it differently. In a textbook treatment, when you see such an expression, one never sees a qualification like the one in the box below written immediately below it. And one might wonder, is it always going to give me meaningful probabilities? And textbook authors, of course, haven't bothered to discuss it. And I think one of the reasons is because the nature of Schrödinger evolution is such that just for practically any reasonable wave function, this current positivity condition is satisfied, I would say. I mean, for typical scattering experimental situations, okay? And this is quantified much more rigorously in the scattering papers. I like to mention the flux across surfaces theorems. There's so many papers by, Detlef, Shelley, Nino, all their students. If some of you are aware, you can look these up, and this very careful analysis of how this condition arises in concrete situations, even sometimes with potentials, without potentials, relativistically, non-relativistically, and so on. So in short, this current positivity condition is extremely robust, and its validity is sort of built into the Schrödinger evolution. And that's why the previous probability assignment is kind of the right thing for all practical purposes. And high energy physicists have been using it all along, by the way. But what we are going to talk about are exactly wave functions for which this condition is violated. And since I said they're very difficult to prepare or produce, we discuss what additional ingredients it takes to arrive at a non-CPC wave function. So CPC stands for current positivity condition, okay? Are there any questions at this point about the motivation? It was a bit sketchy, but tried to be quick. Or comments? Okay, so let me go on. So this is a proposal of Detlef and mine from 2019. So what we looked at was a particle with spin. So why is spin relevant, I will say. I mean, it's actually written on the slide, but I will emphasize in a minute. Because in the case of particles with spin, the probability current is not the same as what's written here. So that's the first thing. And in the current positivity condition, the current matters. So already there is something new coming in the direction of the probability current when you include spin, when you take spin into account. And what we found was if you prepare these particles like so for the whole talk, we just think of electron, okay, as a spin half particle. So if we prepare these electrons in these so-called spin polarized states, meaning they are kind of factorized wave function where all the spatial dependence is sitting outside, let's say, is factored out, okay? So I have been presenting these things in previous talks, so I guess I can just go a little faster over portions, okay? But if somebody has a question, just stop me. So what we found was if you prepare particles in these kind of states, and these angles here, these theta and phi are just parameters, like, so for a particular choice of these angles, you get one wave function, another set gives you another wave function. So it's a class of wave functions called spin polarized wave functions. And what we found is if you take an electron and accelerate it down a waveguide, so a potential which confines the electron in some kind of a volume, cylindrical volume, let's say for simplicity, and if it has such a wave function, then the probability current given according to this formula, so you take these kind of wave functions, plug into this current formula, you end up violating this current positivity condition on any cross section of the waveguide, basically. So what I mean is this, so think of a cross section of the waveguide as your detection surface, and imagine how the component of the probability current is pointing at different points on it. And then there are regions where it's pointing in one direction, and then there are regions where it's pointing in another direction. And what's important is this kind of behavior of the current is very stable in time. So it doesn't get destroyed at the next moment of time. So that's why it's experimentally very promising. And these are things I have said even before, but just wanted to quickly summarize. So in short, to produce backflow, so I would use the word backflow non-CPC because it's just a short name. So to produce backflow, we looked at particles with spin moving in a waveguide. And actually, both these ingredients are extremely important, both the confinement produced by a waveguide and at the same time having spin in the discussion, because it turns out that if you took a spin zero particle, one, let's say, governed by Schrödinger's equation, and you made it move in a waveguide, you won't see this backflow, or you won't violate CPC. At the same time, if you took a spin half particle like an electron and didn't have the waveguide confining it, you would also not see the backflow. So both these ingredients are crucial for violating this current positivity condition. So here is a quick picture that I took from a recent Popular Science article on this. I don't think the writing is very visible, right? Because it's a bit small. I just took a screenshot. But here you have a very quick schematic of the setup we are looking at. So the plan is to have an electron which is initially prepared in some localized state at one of the ends of a cylindrical tube, our waveguide. And at a time that we call time zero, you release the wave packet so that it spreads and propagates into the tube. And the plan, of course, is to record the time instance at which it's detected at a certain distance downstream. So here is a detector. I mean, it's a schematic picture where as soon as you see a click, you record the time. And the plan is to repeat the experiment again and again under identical conditions to collect statistics. Okay.
Can I ask a question?
Yeah.
So using this image, right? You say that the current positivity condition is being violated. The positive current is being violated.
Yeah.
That means that somehow the current is actually flowing through the director, but in the wrong direction. Is like the intuition that I have.
Yeah, that's That's a good question. I think what you have in mind is if there is a detector, why is something flowing back? Is that
Yeah.
what you're kind of worried about? So I must make it clear from the beginning, in these discussions, the detector is not taken into consideration in the sense that it affects the otherwise Schrödinger evolution. I will say more about the detector stuff later. So right now, what I wanted to do is I wanted to create a situation and to motivate. So the motivation is the usual scattering considerations, and we here have an example where these considerations wouldn't apply. And what I'm suggesting implicitly is that considerations going well beyond the standard textbook narrative is necessary now. Whether the detector matters, what's happening, what's not happening. But this is just the story if you go by the evolution given by our wave equations, right? That's, at the moment, that's just my, think of it as a preamble for what's coming next. I mean, I won't be able to say what, I mean, in the presence of a detector, things might become very complicated. So so I won't be able to answer that question if, or maybe I took the question more elaborately.
I think my question is a bit dumber than that, because I think the intuition that I have is that, like, we have in that image, right? We have our particle which has its wave packet located on the left-hand side of the detector, and somehow we find that the current is actually flowing to the left through the detector. And so the question that I have is, you know, the current is supposed to represent our probability density flowing, which means that if our current is moving to the left, then that means that there had to have been probability density on the right-hand side that's flowing to the left. Does that make sense?
Yeah, okay, I see. But by the way, I said also that in certain parts of the screen on this cross section, the current is pointing in the other direction. So it could also be that, you know, the current is sort of circulating. And I mean, so you mean the probability density can still be just flowing out, even though the current is pointing backwards at certain locations, right? I thought we were worried about, is the probability density like flowing inwards or something like that?
Lawrence, and there's not going to be any of this backflow that you're worrying about, and that's important here, until after time zero, until after there is the wave function, part of the wave function has gone to the right of what's called the detector surface here, or this special surface, which is black. Once it is to the right, you know, there could be stuff flowing in either direction.
I see. Yeah, I think that makes a lot of sense. So I think the t is equal to 0 was the thing I was worried about. Or I suppose in for relativistic cases, right? There's, like, you know, the wave function propagates locally. So there is going to be some amount of time before the condition can be violated.
Okay, I see. So you mean, like, what about the finite time of propagation? Is that like the time the wave packet takes to get to the screen or something, right?
Mm-hmm.
Yes, yeah, that's of course the case. So in an explicit example, of course, there will be a certain time after which the wave packet is mostly around that region, and only during those times the backflow is important. But at the moment, you know, I didn't even want to call it a detector. My whole point was, I'm thinking of this as a simple geometric surface that I can just imagine to be sitting there, and all I'm looking at is what's the probability current doing on it. And you can take the screen or the surface closer or far away from the initial wave packet as you like. So it's just a mathematical discussion for the moment.
Yes, I guess Lawrence would like to hear you say yes or no, that there's a perhaps small, but certainly a finite positive amount of time before which there will be no backflow at this piece of surface over there.
And the answer is yes and no both, because it depends on the initial condition. There are wave functions which have, which are smooth tailed. They will give you backflow even starting from t equal to 0 at any distance, as I can show you. And then there are cases where it takes some time to appear. So I don't think the answer would be very straightforward.
Even if the wave function was originally totally inside that region on the left.
No, exactly. So it's exactly these cases where it's totally inside. You need a delay until the wave packet sort of.
I think that's all Lawrence wanted to hear.
Okay. So I was, sorry. I was getting very worried about the detector discussion. So let me move on, okay? So this picture is kind of necessary at this point. What Detlef and I were doing is, for these examples, we were just looking at what's the distribution of the arrival times of Bohmian trajectories of an electron as it strikes what was written as a detector in the previous figure. And we found these amazing distributions, as you have seen several times in my talks in this seminar. There were cases for which the striking times of Bohmian trajectories were distributed well over a big range, and the distribution had a nice tail. And there was a case for which it turned out that the trajectory struck this surface within a certain time that we call Taumax. And this is a very interesting effect. And this is, let's say, a very concrete outcome of the backflow. So the backflow seems like a very mathematical condition about the probability current. But if you sort of try to translate it to a physical signature, and just for a start, say, what if I look at the arrival times of Bohmian trajectories, then a state which violates the CPC condition could give rise to something as beguiling as this red curve. And I have discussed this at length in the last seminar, and now I will move on to relativistic treatment of this setup and these arrival time distributions.
But what's the insert?
The insert was, Shaili, these are the details. So in the initial wave function, it produced ripples after the sudden removal of the front wall, and that led to particles arriving in bunches and so on. That can be a whole talk in itself. So I would just these ripples are the small arrival. These are sort of like secondary lobes of the arrival time distribution, which are appearing at small times. Does that make?
But you have all of those ripples presumably going on forever to the left, but there's a last one to the right. Is that right?
Exactly. So these ripples are produced. They are basically a result of taking exactly a situation where the wave function is tightly in a box. You remove one of the walls suddenly, and then the wave function produces, the Schrödinger evolution just gives rise to these ripples because it's trying to evolve a very compact initial condition, let's say. All right, so actually these ripples would be a whole talk in itself, so I'm not very prepared. So let me go to the next slide. So all so far was a non-relativistic treatment. So, the entire experiment really can be studied very successfully, non-relativistically, and it's very, it just turns out that with various kinds of playing around that one can do by changing potentials, the nature of initial wave function and the shape of the waveguide, like cross-section of the waveguide, all these kind of things that you could change, it turns out that after all these kind of distributions are robust, they always show up. So that was also the reason why we think that there is something to them, and we have been studying them more and more. And then as non-relativistic analysis suffices, really, there is a question, why would anybody try to do a relativistic discussion of such an experiment? So let me say from right away that as of today, I think really none of the relativistic effects matter for the actual experiments, or the kind of time scales and length scales we have in an experiment today. But that having said, there are a couple of reasons why a relativistic treatment is necessary. One is really going back to this probability current itself. So this expression that I wrote down, as you can see, this term here looks very familiar to what we have from the Schrödinger equation, right? This is a term that not many people are aware of. I guess Shelley and a few others are. But what happens is there is a lot of confusion in the literature whether this term should be present or not. And I unfortunately don't have the time to really give you some nice elements of this debate, but I can recommend this article by Mike Wilkes, which is here. You can really see nice discussion about whether this term should be there, shouldn't be there. And in my opinion, it should be there, but you know, there have been derivations in the history of the subject where people miss this term, and I don't want to get into calling names, but because these effects that I was showing you are coming because I mean, they're really coming due to this term, and this confusion whether this term should be there or not really hurts our analysis here. So
Is it not the case, and isn't this what you have in mind, Siddhant? Insofar as orthodox quantum mechanics, as it's usually done, is concerned, it's not a meaningful question whether that term should be there or not. It's just a matter of definition. Insofar as a good formula for arrival times and detection locations is concerned, the question is whether that term gives you a better answer than with that term, you have a better answer than without it.
I was actually saying something rather more literature-ish on this. What I meant was there are many books. I mean, if by orthodox QM you mean what's written in books, then many books actually have this correctly, including LandauLips. I mean, I was just talking about the expression for the probability. I understood your question, because, you know, whether it's this term or not, what changes for you, right? Isn't that what you were getting at? But what I had in mind was there are many publications who don't have this kind of a term. And these publications are about just the current. They're not even talking about physical predictions or anything, right? They're discussing what's the right probability current, you know, in the usual textbook setting.
Don't bother saying what's been meant by the notion of the right probability current. Is that correct?
What they mean? Well, I mean,
from a Bohmian perspective, it's clear what's meant by the right probability current. From an orthodox perspective, it's not entirely clear.
Well, from a Bohmian perspective, if you fix the guiding equation, then the probability current is clear. But normally, you know, even in writing the guiding equation, in practice, one starts from the current, right? And then the discussion starts, what's the right current? Should you take this or that? But then the answer in the end turns out to be, well, it doesn't matter which current you take because the dynamics produced by any is equivariant, right? And then, so any current is as good or as bad for a Bohmian theory, right?
The theory depends on the choice of the guiding equation, that is on the current. Whereas in orthodox quantum theory, in its formulation as usually presented, the current is not in the formulation, it's a defined quantity.
That's a good point. That what's the role of probability current in orthodox quantum mechanics anyway, right? That's what you are. And why would orthodox QM bother about the right current or the wrong current? Is that what you are
saying? That the clearest place where it gets a role is the detection times.
Yeah, but that's again not discussed in textbooks, right?
Well, that's a pity, of course, but that is the clearest place where it would become relevant, I would imagine.
Exactly. But what I was just alluding to is that there is a genuine confusion about how to derive this term correctly, because some people get a factor wrong and so on. So it's a big literature that I'm forgetting bits and pieces of, but this article is really goes into the heart of it. Okay.
Siddhant,
But
correct me if I'm
given all
wrong.
this, yeah.
Just about that current term. Isn't that derivable from the non-relativistic limit of the Dirac current under like this Gordon decomposition procedure?
Absolutely, that's correct.
So if you started from an orthodox quantum physicist started from the Dirac equation, took its non-relativistic limit, they would arrive at this J Pauli that you have here.
Absolutely, yeah,
So
that's
couldn't they
correct.
argue for it just on that basis?
That's also something. You're right. That's probably the strongest argument, and that's also the reason I bought it early on. But then there are people who want a fully non-relativistic derivation of it, and there are such derivations, by the way.
Mhm.
One that I like a lot is by Levi Leblanc. I think Shelley knows him. It's again basically repeating Dirac's procedure for non-relativistic wave mechanics. And anyways, this article really goes into great detail about it. But let me tell you why it matters here, because you see, in many traditional Bohmian description of a spin half particle, the guiding equation is built on only this term. And if, for example, in Bell's treatment, or many people who followed on, you don't see this present. And if you try to do an analysis of the experiment that I was just describing using a guiding equation based on this, you don't have a backflow because it's a different current. It's a current which looks very similar to the Schrödinger current, so there is no backflow. And you don't see these kind of distributions that I am trying to present as promising. And then there's and then, as I was saying, that the whole discussion rests on whether this term should be there or shouldn't be there. I'm just trying to put it more practically, okay? And clearly, there is no concrete answer. I mean, I have had so many discussions with people. One person likes a particular derivation, another one doesn't like it, and when it comes to what are the right expressions for currents and so on, there is really no optimal derivation, in my opinion. So the reason for a relativistic treatment, the first reason for a relativistic treatment was mainly to do the analysis based on Dirac's equation, because the current of the Dirac equation has not been debated since its inception, okay? So everybody, even in the Bohmian textbooks of Holland, Hailey, also Detlef, the expression for the Dirac current is there, and everybody believes that the right guiding equation is based on the Dirac current. And the plan was, if we can analyze the same experiment based on the Dirac equation and the guiding equation derived from Dirac current, that would be great. Of course, I know at the back of my mind that you will see this backflow because that extra term there comes from the Dirac current, as you just said, right? That is one of the reasons. And the other reason was, of course, to have an independent theoretical check. And personally, for me, of course, was the reason to really learn relativistic quantum mechanics and see what kind of relativistic effects we get on and above the non-relativistic results. Okay.
Yeah, that's good. Thank you.
So Shadi said I should keep it basic. I tried, but I'm sure at some point I have failed him. But these are some of the most basic slides for this talk. And if somebody is lost or hasn't seen the equation before, just stop me. So what I have here is Dirac's equation as it's usually written when you want to apply it to concrete examples with a potential. It's already quite different from the Pauli equation and the Pauli wave function for the non-relativistic theory. So, I mean, I was once asked, why is this a relativistic equation? I would give a very cheap answer. I'm sorry that, you have C appearing here, and that's one of the reasons. That's actually not the right answer. But and there is, I don't think I will be able to justify in a short time why this is the fundamental relativistic equation for an electron. Wave equation
V
for an
of
electron.
R,
It's a
clash with
potential. So
relativity?
once again,
Doesn't the V of R, the potential term, clash with relativity? If it's
it does. It absolutely does. So that's why I didn't want to give a long answer to that question. Is it or is it not a relativistic equation? So I'll put it this way, that, the kind of relativistic analysis I'm aiming for is in the same ballpark as taking Dirac equation and applying it to, let's say, the hydrogen atom. Okay. And the kind of accuracy and insights we get there, I'm looking for something comparable here. Okay. And of course, with an external potential, relativity is a bit up for grabs here, right? But that aside, I mean, most of you are familiar with everybody has, I hope, seen the Dirac equation. And this is an equation for a 4-component object called a bispinor. So it's actually a system of 4 coupled equations. And these alpha, beta here are matrices, 4x4 matrices that I've written down here. Of course, there are other choices of these matrices, but this is the so-called standard representation. And this is also the representation in which the non-relativistic limit is best seen, in my view. What's worth emphasizing is that this equation has built-in mass, length, and time scales that I've written down here. This length, h bar over mc, is very famous. It's called the Compton wavelength. And for an electron whose mass is about 10 to the minus 31 kilograms, you see these length and time scales are, exceedingly small. Okay. So this actually explains why it's very difficult to solve this equation numerically. So I'm going to be mostly concerned with solving this equation. So I want to emphasize on these aspects. So you can see, if you have to simulate this equation, the kind of length and time scales it has, it becomes very expensive. You'll have to take a very fine grid and so on. So numerical solution of the Dirac equation is a whole area of itself, as I learned in the last couple of months. And before I go on to show you something concrete, this equation also gives you a probability current through a continuity equation. So here is the expression for the current. And as I was just saying, this is not really debated as far as I can tell. Nobody that I'm aware of would think that something else is a better expression for the current other than this. There are many nice properties this current has, and if you look at the PhD thesis of
you
Watts,
really want the curl there, or do you want a divergence?
there is a mistake here. I'm sorry. Thanks, Shirley. This should be a divergence. I don't know why it's a curl, so it should be a. Thanks. I was actually expecting something totally funny here. Sorry about this. Anyways, and one of the nice things about this current is if you define a Bohmian velocity in the usual way, you get, so at every point along the trajectory, you get a velocity which is less than or equal to c. I mean, this is an identity. You can do the Dirac matrices algebra, and you can conclude that the absolute value of the current is always bounded by c times the density. So the Bohmian velocity is time-like. It can become light-like at a few points, but in general, it's time-like. So it has all the kind of right proper. I mean, it has many other properties that I don't have the time to discuss, but it became clear early on that this has all the right kind of properties to have a single electron Bohmian theory built it has all the right ingredients for a single electron Bohmian theory. All right, and just a quick comment about the non-relativistic limit. This should be done very carefully, but in a physics style, if you heuristically think of C going to infinity, then what happens is these lower components of the solution become subleading, and what survive or are in the leading order, these larger components, and these two component object now is exactly the non-relativistic wave function that we were talking about a while ago. And this two component guy satisfies a non-relativistic wave equation, Pauli equation. Okay. And also in this non-relativistic limit, this current, which is a very simple expression, reduces to that huge expression with the spin term and so on. Okay. Are there any questions here? I was just.
Isn't it interesting that here you have a current without any derivatives in it becomes one that involves derivative?
Yeah, that's also going back to this. So this was a concern in the early days of the Dirac equation. So in the very same year as of in 1928, Gordon tried to again do this gymnastics with Dirac matrices and rewrote this guy as a sum of a gradient plus another thing, but that another thing was not a curl, by the way. It only becomes a curl in the non-relativistic limit. So basically Gordon decomposed this compact expression into something that looks familiar, like the Schrödinger current plus something else. And this appeared within months of Dirac's first paper, by the way. And it goes by the name of Gordon decomposition. So in that decomposition, you can rewrite this with derivatives and so on. Right? Okay. I want to make a comment about solving the Dirac equation because we'll be talking about solutions. And I must say, this was one of my longest research journeys. Like, had been working on this since almost 2018 sporadically because it was just not working out. The goal was to find solutions of the Dirac equation with this tube so that we can do an analysis of the arrival time experiment. But I mean, there was just dead end, whatever I was trying. And the reason really is this equation is very difficult to solve. I mean, not just for me, but in general. And if you look into the literature in 3+1 space-time dimension, there are hardly any wave packet solutions. So when I say wave packet, I really mean a normalizable propagating thing, right? Like a Gaussian wave packet, for example. If you look at Greiner, for example, the very well-written and important textbook of relativistic quantum mechanics, he has a whole chapter on wave packets of the free Dirac equation, free meaning without any potentials. And you read the discussion, it comes up with so many complicated integrals, and then he leaves them uncomputed. And he makes some remarks as to why is it difficult and so on. In the literature, it's not many wave packet solutions are known. And just for free particle, I know of 2 papers which give them. So already for the free Dirac equation, I'm suggesting that it's very difficult to get wave packet solutions. So with a potential like our waveguide, one can imagine why is it very tough. And although there are solutions of the Dirac equation which are not wave packets, they are these famous stationary solutions, which have this particular kind of time dependence. And there are many examples, and there are a whole textbook collecting these solutions. The first one was Coulomb potential. Dirac himself treated this problem, although he didn't have analytical solutions, but they were soon found by Gordon and Darwin and many authors afterwards. Then there is solution for the constant magnetic field. One of the guys who found this early on was Rabi. And there are solutions for an electron in a plane electromagnetic wave potential found by Volkov. And there are a few others, by the way. So this was just to say why this journey was quite difficult. And I want to also emphasize on the problem created by 3+1 dimension. I mean, in the literature, it's you can see many articles on the Dirac equation in 1+1D, 2+1D, and so on. And of course, they of course emphasize certain features of relativistic wave propagation. But there is I mean, this is a very simple observation, but it makes a interesting difference for solving in non-relativistic QM and solving in relativistic QM. So in non-relativistic QM, you know, if you have a potential which is of the form some f of x times plus g of x plus some h of z, sorry, f of x plus g of y plus h of z, then, you know, you can solve the Schrödinger equation by separation of variables. And then you get basically one-dimensional Schrödinger equation for each of these contributions to the potential. But in the case of the Dirac equation, if you take the very same potential, which has this additive form, and plug it in, you cannot solve that equation by separation of variables anymore. So that's, and you know, that's really the only technique one has to begin to start solving, and that itself fails in the case of the Dirac equation. So the equation couples components in such a complicated way that some of our very favorite techniques don't work. And that's why I think some of the insights gained from one-dimensional or two-dimensional solutions of the Dirac equation really do not carry over, at least to my satisfaction, for a full three-dimensional consideration. All right. Are there any questions so far, or none, it seems? So let's talk about situations with cylindrically symmetric potentials. I mean, that's of interest for our experiment. We want to have a waveguide, which is a cylindrically symmetric or axisymmetric situation. Now, now for these kind of potentials, the Dirac equation has also been extensively studied. I will give you references below, but one article which really summarizes what can be done, what cannot be done, is this article, and it's quite good to read. In short, it turns out that there are only two potentials, electrostatic potentials, for which the Dirac equation is solvable. By Dirac equation, I mean, again, stationary solutions, right? I don't mean wave packets. I mean, even solutions of these kind can only be found for two potentials. One is a constant potential, which is as good as a free particle, and another non-trivial potential, which looks like the Coulomb potential, but this rho is the cylindrical radial coordinate. So it's like an attractive potential, which is singular on the z-axis. Okay. Now, at one point, I was trying to cook up waveguides by piecing together piecewise constant potential. So think of like a finite square well. So there is a cylinder inside which, let's say, the potential is 0, and outside it's like a finite constant, you know, like particle in a finite square well, and a few other examples. And these led to very complicated equations due to the boundary conditions, and that didn't lead anywhere, and I had to just leave it almost from where I started.
Siddhant, are you familiar with the Chandrasekhar separation?
Yeah, for the black hole, you mean?
No, for Dirac's equation. So Chandrasekhar has a way of separation of variables technique that he applies to Dirac equation on uncurved space-time. But I was wondering if that technique can be used to treat potentials.
I'm only aware of Chandrasekhar's solution for one of the black hole geometries.
Yeah. So that's the technique that he uses there. That's what I'm referring to.
Yeah, you can set the gravitational constant equal to 0, right? So that doesn't change the separation of variable techniques. It actually simplifies it.
I see. But is it for a cylindrical geometry?
No, it's in all.
Or you are suggesting that maybe one could.
Well, it's when you think, for instance, of the Kerr solution. The Kerr solution has axisymmetry, right? So axisymmetry is comparable with cylindrical symmetry. You would have.
I always have to ask. So this one is the charged black hole, the Kerr one. Right?
Kerr-Newman is charged rotating, and Kerr is
okay,
just, and without charge it's Kerr. and but it has, because it's rotating, has axisymmetry, and that separation of variable technique should work for you also in a cylinder, no? Even though you may not have a rotating cylinder.
So I'm just writing it down just for. As far as I know, one of the authors, his last name was Vilalba. I don't remember the first name. He extensively looked at general factorization of the Dirac equation, cylindrical geometry, and even since then, these are the only two cases which could be solved in terms of standard special functions, for example. But if there are
Here,
more
rho is
examples,
what?
I would love to know.
Rho is what here?
It's a cylindrical radial coordinate, square
Okay.
root of x squared plus y squared.
Right. Okay.
Anyway, just maybe there is something,
Yeah.
maybe not, who knows?
Yeah, maybe more. Yeah. So,
Okay.
all right. So with this kind of material that's available, I wanted to construct wave packet solutions for the Dirac equation with a tube. All right. Okay, now how do I get rid of this dot?
What dot?
There used to be a clear, this purple dot that I drew.
It's okay. Don't worry about it.
Okay.
We ignore it.
Clear. Thanks. So I'm going to present two models of waveguides for which I could obtain solutions actually only recently. And based on these I want to carry out the arrival time analysis in the future. The first model is, one might call, or I like to call it a bit, it's like an act of desperation, because I'll tell you why I call it that way in a minute. And the other model is more realistic and more recent. This first model is basically the closest analog of particle in a square well, like infinite. I'm just worried if somebody says don't put infinite potentials into the Dirac equation, that leads to a whole discussion. But I wanted to basically have the closest analog possible of a particle which is moving freely inside a cylinder, like a hard cylinder, and where the potential goes to, let's say, infinity at outside the cylinder. Okay. So the plan was to solve the Dirac equation, the free Dirac equation without any potentials, which I've written here, inside the cylinder, and then somehow ensure that the solution is always contained in this cylindrical volume. Okay, so that if you normalize it once at time 0 inside the volume, and let's say set it to 0 outside, it shouldn't leak out as time goes on. And that could only be achieved with a boundary condition. And the standard boundary condition for doing this is to require that the component of the probability current perpendicular to the surface of the tube, you want it to vanish at all times. And I wrote down expressions for the current. So the boundary condition is written below. So we want to ensure that we solve the free Dirac equation subject to this boundary condition. And also some initial condition, like something which is, let's say, well localized here in this region at time 0. Okay. Now this boundary condition itself connects us to another
Why
stream
did
of the
JZ have to be 0 at the boundary?
which one?
Z.
This Z equal to 0. So I'm actually evaluating the current.
Only at Z equals 0. That's fine. Thanks. Yeah.
Yeah, it's just the XY plane, the end face of the waveguide. So here, I would love to talk about the various different proposals one has in the literature for realizing this boundary condition. That's a long talk in itself, but it's all discussed in this recent quick article that I have put up. I think Shadi would be very interested in this discussion of different boundary conditions. But
Siddhant,
from,
yes, I'm very
you know,
interested, but just to let you know that the time is running out, so I think you may want to
yeah, so that's
wrap
why
up.
skip. Yeah, so so I chose a particular boundary condition, which is just to set the upper components of the solution to 0 on these surfaces, so on the walls of the waveguide. This is enough to ensure that the current vanishes on the boundary. Okay. And there is physical motivation for it, which I have tried to present here. As I was saying, for inside the tube, we need to solve the free Dirac equation, and the Dirac equation is solvable for a constant potential, like constant equal to 0. And these are solutions that have been known for a long time. These are two classes of solutions which in the non-relativistic limit reduce to the so-called spin up and spin down wave functions. You can heuristically see that the denominator here has a c square and there is a c here. So, you know, again, when c goes to infinity, everything here goes to 0 basically. And what survives are these guys, and they are the non-relativistic wave functions. I won't, I'm not sure if you're interested in the details, but I'll just speed up a bit because I want to quickly get to backflow. But again, you know, k perp and k, these are just real parameters. So they can be freely chosen as long as the e here is given by this formula square root, this square root formula, then it will always satisfy the Dirac equation. Okay, the free Dirac equation. All right. So here I have tried to satisfy the boundary conditions. So remember, the boundary condition was that we want the upper components to vanish on the walls of the cylinder. Already this sign kz vanishes at z equal to 0. So that's fine. And then on the walls of the cylinder, that is when the radius of when the radial coordinate is a, which is my radius of the cylinder, I want these Bessel functions to vanish. And that happens if you choose this k perpendicular to be one of the Bessel function zeros divided by the radius of the cylinder, right? So basically, this gives you various modes, as one says, right? You know, for different zeros of the Bessel function that you choose, this k perpendicular takes different values. And for each k perpendicular, you have these kind of solutions which are completely trapped in the cylinder. Okay. I hope that was not too quick, but if there are questions, please ask. So from here on, k perpendicular is fixed for us. And I prefer to take the lowest mode which satisfies this boundary conditions. Okay. All right. So now from these kind of wave packets and by applying boundary conditions, we can construct normalizable wave packets in the usual way. By the way, I should apologize already for using this kind of notation. I don't know if Shelley noticed, but you know, one uses this ket vector for the abstracts, the state vector, whereas what's written on the right-hand side is an explicit representation of the state in position coordinates. So I'm just aware of this, but it's something I'm doing to avoid writing huge formulas. All right, so the plan now is to take some suitable coefficients, these a of ak, let's call them, and integrate against these states. And if these AKs are suitably chosen, something which decays for large K, then the resulting wave functions are normalizable. This is what we do all the time. And it turns out that by picking up either the 1, 0 or the 0, 1 case, you end up getting two classes of wave packets. And I have highlighted certain things here. I will explain in a minute. So these states, which I have written with up arrow and down arrow, in the non-relativistic limit reduce to the familiar spin up and spin down wave functions. In the non-relativistic limit, all these lower terms vanish, and what remains are the upper terms. And what's nice here is that the most general form of the wave packet built from these kind of modes that we were discussing has this rather, I would say, rather nice form. It is expressed, so these J0, J1 are Bessel functions, and this F and G I haven't specified yet, but in terms of just two as yet unspecified functions, F and G, you have, let's say, exact wave packet solutions of the Dirac equation. I mean, of course, I should tell you what F and G are to claim that they're exact solutions, but this is the form of the solution. It's already fixed at this point, okay? And F and G are, of course, very unfortunate integrals, which took considerable long time to solve. And I will show you some explicit cases where F and G can be solved. But other than the fact that these are difficult integrals, what I like at this point is that we have some control on the form of the wave function, and hence we can even discuss what happens to backflow. So as long as we don't specify F and G, we are kind of initial condition independent, right? The specific initial condition that you set at time 0 kind of fix your F and G. And I would like in the next 1 or 2 minutes to quickly show you how backflow arises in an initial condition independent way. Are there any questions so far? Maybe I rushed up a bit in the last couple of minutes.
I'm afraid we are running out of time, so I think you should go ahead and present your final result.
Exactly. So in order to discuss backflow, I took a further superposition of these kind of states, this up and down. And, you know, you can say this state has an explicit form which looks like this. What's highlighted here, what's highlighted in red are the two upper components of the solution. And they exactly look like our spin polarized wave function from the non-relativistic treatment, these. So we are in good shape because we know that in the non-relativistic limit, the lower components will disappear, and that's good news. Now, to discuss backflow, I just computed the component of the current which is parallel to the tube, which means, or the one which is perpendicular to the cross section of the tube, the Z component of the current, which is given by this. And at the moment, this is the exact expression for the current without any simplifications. Why I emphasize on that? Because this term which is put in box is exactly the first term of the Pauli current that I was showing you. And the stuff in red here is exactly what reduces to this spin term in the non-relativistic limit. And I want to emphasize this red stuff is not a curl of something, okay? So this whole current is the complete Dirac current that comes out from just plugging in the wave function and doing some simplification. And that's relevant for our discussion. And then, of course, the discussion will be difficult if I don't specify F and G, but if I specify F and G, we become sort of tied to a particular example. So it was optimal in view of the fact that this Compton wavelength is very small to consider a cross section of the, so to look at distances large compared to this lambda bar. Look, this is really close to a nucleus size. So any distance is large compared to it. And by using, you know, stationary phase kind of arguments, one can find an asymptotic expression for this current that I was showing you before. It's a mouthful, but what's relevant is this stuff in red. And this, the stuff which is highlighted here does not depend on F and G, as you can see. So that means the sign of the current, as decided from this leading order approximation, only depends on the terms in square brackets. And that stuff doesn't depend on this A. You know, the A was here, which was in the definition of F and G. So as long as our discussion doesn't depend on A, it doesn't depend on F and G, and hence it doesn't depend on the initial condition. So all we need to do is look at under what conditions does this square bracketed stuff become negative. Well, I must say that all the stuff outside the square bracket is positive. So the sign of JZ is decided by stuff in the brackets, okay? Again, with some Bessel function work, it turned out that a sufficient condition for the bracketed stuff to become negative is this. This actually was a very important expression for me because it took quite some time to arrive at this. But the right-hand side shows you all the parameters of the problem. A is the radius of the cylinder. L is the distance at which you're looking for backflow. T is the time. J01 was the zero of the Bessel function, and so on. And theta and phi are parameters at the spin angles that we put in the superposition. This inequality here, if you plot it, so the picture below is a cross-section of the cylinder at which I'm coloring regions which satisfy the inequality, and in white are regions which don't satisfy the inequality. And you can see that there is a permanent region at which JZ is negative, which is shown in red here. By the way, it turns out as time goes on, this term becomes very small. So as time goes on, the regions of backflow only grow. It turns out that for sufficiently long times, exactly on half the cross section of the cylinder, you have JZ positive, and on the other half, JZ negative. So that's what I call stable backflow, and it comes out even from the Dirac current without any ambiguity about the current and so on. So I strongly think that this setup will lead to something interesting. I guess time is up, but I wanted to show you some explicit solutions.
Well, let's
but if there are
first,
questions, I can just.
Let's first stop and thank Siddhant for very interesting talk. And we do have time for some quick questions.
Okay.
So Siddhant, am I right that you so you have shown that backflow, and this is these solutions have backflow, and they have it at large distances from the source, because these
That's
formulas
correct,
are
but it's
derived
only
under the
large compared to the
assumption
Compton wavelength.
That's what I mean. Yeah.
Yes, and here large is like any distance, I would say, physically.
Yeah, I understand. Yeah.
That's correct. So independent of the initial, the initial condition is only constrained by normalizability and so on.
Right.
Other than that, you have backflow. And it actually becomes stable in time, and that's very important for experiments.
Right,
because if it just,
okay,
if the regions of backflow disappear, then you're in trouble.
But doesn't this mean that this way of measuring the arrival time is not correct?
Well, all I was trying to allude to is the positivity of current is very important in scattering. So all the formulas rest on that. As soon as you have even an example which shows stable backflow, one has to wonder what to do next. And
right, and what is your answer to that?
I don't think there are any recipes. Well, I think the Bohmian trajectories give us something reasonable to start with. One could improve the analysis maybe by taking detector models into account and so on. But that's the next step. First, one should be sure that here is an interesting example.
Mm-hmm.
And this backflow and its stability has not been there so far in the literature, right?
Mm-hmm.
So I'm trying to say for today's talk that this is a setup where one should be investing in. And whatever you think is the right, or whatever turns out to be the right answer, it will definitely deviate from the standard quantum mechanical kind of answers one sees in the scattering literature.
I see.
That's already
so your goal, am I
amazing.
right that your goal right now is to tell everyone that there is a problem, there is something that direct people's attention to, there is something fundamentally problematic with this
Yeah, so for the arrival time, that I do in a slightly different way by basically comparing all these different guys, as you know. But here I'm trying to go a step further, that this is, the ultimate challenge, does your recipe work for this backflow situation? Some would say yes, some would say no, and then experiments should be done to decide what's going on.